Okay, we're going to start here with an application problem, but many relationships will follow exponential laws of growth. An example is where the rate of variables changes is directly proportional to the variable. So for instance, suppose that we know that the rate that y changes with respect to x is directly proportional to y. And we also know, suppose we also know the value of y at t equals 0 is y naught. So what we could do here is we could actually write this, multiply both sides by dx here, and then after that divide both sides by y, and we would get dy over y is equal to k dx. Okay, so then we could integrate both sides. So if you integrate the left hand side, you get natural log of the absolute value of y, and we won't worry about the constant since we're going to add it over here. And then on the right hand side, when you integrate the constant k dx, you get kx plus c, and where c is actually the constant of integration. Well, you can actually write the equation in exponential form, because since you know here the base is e, then you can say e to the kx plus c is equal to the absolute value of y. But since we know that this can never be negative, it's got to be greater than 0, then we can get rid of the absolute value and just write it like this without the absolute value. Okay, now using your laws of exponents, you can actually write this e to the kx plus c as actually e to the kx times e to the c. And since e to the c is actually a constant value, we'll just replace e to the c with a letter called a, and then we can have, then y would equal a times e to the kx, where a is a constant. Now, we also know that if x equals 0, you could let x be 0 here, and then you would get e to the 0, which is 1, so y would equal a. So since we know that when x equals 0, then y equals a, we can actually refer to a as a naught, or the initial value for y. So then we could get the formula that y equals a naught e to the kx, where a naught is the initial value of y, or if you don't like the a, you could write that as y equals y naught e to the kx, where y naught is the initial value. Now this formula has been written several ways. You can see I wrote it like y equal y naught e to the kx, but if the independent variable was time, you could write it as y equals y naught e to the kt. If the independent, and also if you're dealing with populations, you might write it as p equals p naught e to the kt. If you're dealing with money, for continuous compounding, you might write a equals a naught e to the rt, or actually sometimes they use p here for principal. But this is actually known as the law of exponential change, and the function is actually increasing if the constant k is a positive number, and it's decreasing if the constant k is a negative number. So with exponential growth, there's two types of exponential growth. There's unlimited exponential growth, and that's when you assume that the population will just continue to get larger and larger regardless. So, but then there's another type of population growth called the logistic growth model, and in the logistic growth model, then your population growth would actually level off after a certain time. And that makes sense for certain populations, like populations of animals, where they grow exponentially for a while, but then they begin to level off because there's not enough food for the animals to survive, or maybe they're being killed off by predators. So we're going to just focus on, I said I would talk about logistic growth later, but I don't even know if I have one of those in this lecture. Okay, so we're going to focus on exponential growth. So let's look at an exponential growth problem here. Okay, so let me just show you, start right here. The number of people cured, let's say the number of people cured is proportional to the number that have the disease. Suppose that in the course of any given year, the number of cases of a disease is reduced by 20%. If there are 10,000 cases today, how many years will it take it to reduce the number to 1,000? So what we've got to do is we've got to find y0 and k, and then we need to find the time it takes to reduce the function to 1,000. So I'm just going to use y equals y0 e to the kt. Now, since the initial value is 10,000, we're going to just go ahead and plug 10,000 in for y0. So we get 10,000 e to the kt. So it says that in 1 year the population is reduced by 20%. So let's let t equal 1 year, and we know that in 1 year the population drops 20%, and 20% of 10,000 is 2,000, so we'll only have 8,000 after the first year. So what we can do is we can put in 1 here for t, and then that'll give me e to the k. So that would give me e to the k. That should be a k right there, not a t. Okay, so let me fix that real quick. Okay, so as I said, that should be e to the k. So letting t equal 1, you get e to the k, you get 10,000 e to the k. So here we have 10,000 e to the k, and then we know when t is 1, the y value, or the population, would be 8,000. Now we can divide both sides by 10,000, and then we isolate the e to the k, and then so that would mean that e to the k is equal to 0.8, and then if we take the log of both sides, we get the natural log of e to the k is equal to natural log of 0.8, and the natural log of e to the k is just k, so we know k is the natural log of 0.8. So now we can get our completed model. So go back up in here, replace this k with natural log of 0.8, and we get our completed model. Y equals 10,000 e to the natural log of 0.8. Now what we can do to answer the question is we want to know what's the time value for when the population reaches 1,000. So we can plug 1,000 in for y. So we'll put 1,000 in for y, and then we'll solve this for t. So we'll solve this similar to how I solved for k a minute ago, but this time we're solving for t. So divide both sides by 10,000 and you get 0.1, and then take the log of both sides. So if I take the log of this side, I get natural log of 0.1. If I take the log of this, I actually just get the exponent, natural log of 0.8. And then to solve for t, natural log of 0.8 times t, and then just divide both sides by natural log of 0.8, and that will give you your t value. So I used a calculator, and I got about a little over 10.3 years. Okay, here's another example where I give you the population formula. So I give you this formula: A equals 5,000 e to the 0.001 t, where A is the population and t is the time in years. So to find the population in the 5 years, I'll let you look at that. That's pretty easy. You just plug 5 in for t and then grab your calculator. But the next question says, how many years will it take the population to double? So what I'm going to do, since we know 5,000 is the initial population, I'm going to set A equal to 10,000 so that I can double the population. So I have 10,000 equals 5,000 e to the 0.001 t. Then divide both sides by 5,000 and you get 2 equals e to the 0.001 t. And then apply natural log to both sides. You get natural log of 2 equal natural log of e to the 0.001 t. And then natural log of e to a power is just the power. And then to solve for t, divide both sides by the 0.001. And so you get the natural log of 2 divided by 0.001 is a little over 693 years for your answer. An interesting fact is if you searched online for population clock, you would actually find models that model everything from the world population to the to the number of barrels of oil that's consumed per year. So, and then you can also find things about when the like the number of people that died to cancer or died because of certain diseases and so forth. They've pretty much put everything on a function, exponential function. But if you get time, just search population clock and you can find that. Okay, so look at this one real quick. In 1900, the population was 12,500. 20 years later, the population was 16,000. And so what I'm going to do is I'm going to show you how to create the model. So I'm going to actually use a model like P equals P naught e to the KT for P for population. Now, since I know the initial population is 12,500, then my constant for P naught would be 12,500. Okay, now what I'm going to do now is, since I know in 20 years the population will be 16,000, what I'm going to do is I'm going to put 20 in for T. So that'll give me a 20 right there. So I have 12,500 e to the 20k. And then when T is 20, then the population is going to be 16,000. And now I'll let you solve this, but basically just divide both sides by 12,500, then take the log of both sides, and you'll actually get your K is natural log of 1.28 over 20. And actually there should be another 0 there. So that should be 0.01234 approximately. So it's correct here. So the model, once you put K into your model that we had up here, you'll get 12,500 e to the 0.01234 t. And so there's your model. And then B says predict the population of the year 1950. So that's the easy one. All you have to do is plug 50 in for the t value and then grab your calculator and see what it equals. But the next one says, when will the population reach 37,500? So on that one, we actually let P equal 37,500 and solve for T. So if you put 37,500 for P and then you solve this for T, you would actually have to divide both sides by 12,500, so that would just give you 3. And then you would take the natural log of both sides, and you get natural log of 3 is equal to 0.01234 t, and then divide by 0.01234, and you'll get t, which is about 89 years, or the year 1989. Now go ahead and look at this last one. I may not finish yet, but look at this last one. This talks about the half-life. So it says the half-life of radioactive material is 20 years, and we start with an initial amount of 80 kilograms, and it says construct an exponential model that gives the material remaining after T years, and then how much of the material will remain after 200 years. So I'm going to use A equals A naught e to the KT as my model. I know the initial value is 80, so I can put in 80 for A naught, and then we know that the fact that A equals 40 when T equals 20, because since the half-life is 20 years, I know that the amount will drop to 40 when T is 20. So then what you can do there is put in 40 for A and 20 for T, and then solve for K like I did on those previous problems by isolating the exponential and then taking logs. So there's my K value, and then you can go back here and plug the K back into the formula. And then the next question just says how much of the material will remain after 200 years. So you take this model, replace T with 200, and then it's going to give you an answer as 0.078 kilograms. So, and theoretically, it never all decays. Okay, so on the next video, I'm actually going to start with some compound interest formulas. So I wasn't able to finish the applications on one video, so I'm going to throw in another video of some other application problems of exponential and log functions. So be sure and check out the next video.